Hey, good morning, geometry fans. Here we go again. We're going to talk about perpendicular bisectors and angle bisectors of triangles today. This is lesson 14.3. Some of what we're doing will be from the book, and some of it will not be from the book. Take a moment, take out a sheet of graph paper, and graph the triangle that has the coordinates that I have listed here. Let's call this one point A, this one point B, and this one point C. So go ahead and pause the video and plot the triangle with those coordinates as vertices. All right, so there we've got triangle ABC. Nothing terribly exciting about that triangle. What we want to do next is locate the midpoint of each of the three sides. So we want the midpoint of segment AB, the midpoint of segment BC, and the midpoint of segment AC. You might recall we've got two ways of handling that. We can count and find our midpoint, or we can use the midpoint formula to find our midpoint. So I'll go ahead and remind you what the midpoint formula is. The x coordinates of the midpoint, we take the two x values, add them together, divide by 2, and for the y coordinates of the midpoint, we take the two y coordinates, add those together, and divide by 2. And so then that gives us the coordinate of the midpoint. So again, pause the video, take a moment, and find the midpoints of those three sides. So there are my midpoints. I have them plotted. I've labeled them M1, M2, and M3. The coordinates of M1 are 1, 2, 3, 4, 5, 6, 7, -2. The coordinates of M2 are 1, -6. And the coordinates of M3 are 0, -2. So the next thing we want to do is we want to draw a line through each one of those midpoints perpendicular to the side that it's on. So let's start with M1. So we want a line that goes through point 1 but is perpendicular to this line. So you might ask yourself, well, what's the slope of this line? So the slope of that line is 1, 2, 3, 4 over 1. So that's a -4. So a perpendicular slope, who remembers how to perpendicularize a slope? That's right, you turn it upside down and change its sign. So that slope will be positive 1/4. So up 1 over 1, 2, 3, 4, and we could put a point right there. So from M1, we're going to rise 1, run 1, 2, 3, 4, and there will be a point. If I go the other direction, go down 1 over 1, 2, 3, 4. So I want to draw a line that goes through those points, and I'm going to go ahead and keep my line purple here. So that's not very good. So I'm going to try again. So something along those lines. Now, to go through M2, we're going to have to be perpendicular to line AB. Line AB is horizontal, so perpendicular to horizontal will be vertical. So that line will look something like so. And then perpendicular to AC, if you go ahead and calculate that, will be something like this. And then notice that those three perpendicular bisectors all met right here at a point. That point has a special name, and the name of that point is the circumcenter. So there's a useful property of the circumcenter, and I have added a circle to the picture, And the interesting property of the circumcenter is it will always be the center of a circle that circumscribes the triangle. So there's a lot of words there. Notice that the triangle, all 3 points of the triangle, all 3 vertices of the triangle are on the circle whose center is at the circumcenter. And the circumcenter is the point where the perpendicular bisectors of a triangle meet. Whew, that's a lot of mouthful right there. All right, guys, our last point of concurrency is called the incenter. And the incenter is the point where the angle bisectors of a triangle meet. So I'm going to take a straight edge here and just kind of pretend to bisect each one of these angles. So I'm just going to try to draw a segment that cuts the angle in half. So I'm just trying to make this angle and that angle equal. So that looks to me about like right about there. Now I'm going to try to do the same with this top angle. I'm going to try to cut this angle in half using a straight edge. So here I go, roughly cut in half, and then lastly with this one, roughly cut in half, and lo and behold, those 3 segments all meet at the same point. So what we're saying here is that these 2 angles are congruent, these 2 angles are congruent, and those 2 angles are congruent, and this point, his name is the incenter. And the incenter also has a useful property. It is the center of a circle that is inscribed inside of a triangle. So basically what that means is that right here, the triangle and the circle intersect. Right here, the triangle and the circle intersect. And down here somewhere, the triangle and the circle intersect. Now, if we think about what it means to be an angle bisector, if I needed a point inside this triangle to be the same distance from this side as it was to this side, in other words, I want to be walking along a road here so that the road is the same distance from that side and that side, then I would need to be on an angle bisector. And likewise up here, if I needed this distance and this distance to be the same, then I would need to be on an angle bisector. And so then the angle bisector meets at the centroid, and in all of those points, the distance from that point to the circle is going to be the same distance. So whatever that distance would be, that is the radius of the incenter.